Hi, my name is Gary Waldo. I'm a product planner with Tektronix in our Scopes organization, and I'm very proud to introduce you to the world's first mixed domain oscilloscope from Tektronix. What we've done is we started with our existing MDO4000 series in the mid-range. We compacted the front panel a little bit here to make room for a new section over here where we added a dedicated RF input, dedicated spectral controls here. So of course we have the RF input, but in addition we have the 4 scope analog channels as well as 16 digital channels, making this up to a 21 input system or 21 input oscilloscope for complete system visibility. Now, because we've taken both the frequency domain and the time domain and integrated them into a single instrument, we have the ability to provide a time-correlated view of analog, digital, and RF in a single instrument. I'm going to demonstrate that here. What you see on the top of the screen is a typical time domain display where we have probed several signals. I'll get into those in a second. And then in the lower half of the display we have a frequency domain view of what's coming in on the RF input. So the signals we're looking at here, we're looking at the power on of a voltage controlled oscillator and a phase lock loop. Channel 1, the yellow signal here, is probing the control signal telling the VCO when to turn on. So this rising edge right here is when the VCO turns on. Channel 2 is the phase lock loop voltage, and then I'm using 3 digital channels to probe an SPI bus that tells the VCO PLL circuit what frequency to tune to, which in this case is 2.4 gigahertz. Now, the way we correlate the views between the domains is through something we call spectrum time. Spectrum time is indicated by this orange bar right here and represents the period of time that this spectrum shown in the frequency domain came from. So that means this view of the spectrum came from this precise period of time right here before the VCO has turned on. So as we would expect, because the VCO is not turned on yet, we're basically seeing noise in the frequency domain. Now, we can actually move spectrum time through what I call analog time by turning our wave inspector pan control here. So I'm going to move it over just a little bit. You see there's still nothing there as the VCO hasn't turned on yet. I'm going to move it a little bit more. Now notice that we've moved spectrum time past the rising edge of the VCO, so the VCO is turned on and it comes on at 2.57 gigahertz. Notice that that's automatically marked for me as well. I don't have to do anything to see that. It's just automatically the peaks are marked. If I move this over a little bit further, now it knows what frequency it needs to tune to, which is 2.4 gigahertz. And as I turn this control, you'll see spectrum time move through analog time and watch the spectrum update. So notice that it starts tuning towards 2.4 gigahertz. And all of this is being done on a stopped acquisition. So in a single acquisition, we acquired this transient event and are able to completely analyze it in a stopped state and view how the spectrum is changing over time. Another key thing to take away is the span. Our span right now is 400 megahertz. A typical spectrum analyzer can only capture 10 megahertz capture bandwidth at a time. In this case, we've captured 400 megahertz span in a single shot event, which is enabling us to see what the RF is doing over a very broad range of the spectrum. So again, I'll continue moving spectrum time here. And we see that it actually undershoots the desired frequency of 2.4 gig and then starts to come back up. And finally there, we've settled at 2.4 gigahertz. I can quickly tell just by looking at my time per div here that this is approximately 320 microseconds from when the circuit turned on to when it achieved its desired frequency. There is no other instrument in the world today that can provide these types of views of analog, digital, and RF in a single instrument.